In our last lesson, we reviewed what the first and second derivative tell us about function behavior, where we have intervals of increasing, decreasing, relative extrema, concavity, up or down, and inflection points. Today, we're going to take all of those ideas and we're going to tie them with some other things that we've learned in other math classes and earlier this year to come up with a complete picture of what's happening with the function. So we're going to find the intercepts, the symmetry, the asymptotes, intervals where x is increasing and decreasing, intervals where x is concave up and concave down, relative extrema, and inflection points, justifying each answer. Then we're going to use all of those things to tie them together to come up with a graph of what the function would look like. So we have f of x equals x divided by the square root of x squared plus 2. I'm going to start with intercepts. Specifically, I'm going to start with the x-intercept. And if you remember, the x-intercept is where our y value or our function value is equal to 0. So I want to know where is x divided by the square root of x squared plus 2 equal to 0. And we said before that the only way a function could be equal to 0 is if its numerator is equal to 0. So we have x equals 0. So our x-intercept happens at the point where x is equal to 0. For our y-intercept, we're looking for where our x value is 0. So to find our y-intercept, we'll put 0 in for x. So we get 0 over the square root of 2, which is 0. So our y-intercept is also at 0. In other words, our x-intercept and our y-intercept both occur at the same place here, at the origin, 0, 0. Now we want to take a look at symmetry. And to test for symmetry, we have two different types of, well, really three different types of symmetry. We have y-axis symmetry, x-axis symmetry, and origin symmetry. Y-axis symmetry is going to occur in even functions. To have y-axis symmetry, what that means is that you will get the same thing for f of negative x as you will for f of positive x. In other words, if I put in the same x value, positive or negative, the function value is going to be equal. So in that case, we have an even function or y-axis symmetry. Odd functions happen when we take f of negative x and we end up with negative f of x. So if we change the sign of the x value, we get the same function value except with its sign changed. That happens in odd functions, and we say that they have origin symmetry. Now, the third type of symmetry we don't usually check for, especially if we already know that we're dealing with a function, and in this case we know that we are, but we could have x-axis symmetry. X-axis symmetry occurs if negative f of x gives you the same value as f of x. So the same x value gives you both a negative and positive value, function value that are equal to each other. In this case, we would have x-axis symmetry, but this would not be a function. It would fail the vertical line test. So that one we usually omit if we know that the function is, or that the relationship is a function. So let's see if we can use that to determine what kind of symmetry we have. Notice that whether we have even or odd, we can check f of negative x. And if we get f of x, our original function back, we know it's even. If we get negative f of x back, the opposite of our original function, we know it's odd. And if neither of those things happen, then we don't have either of those types of symmetry. So I check by looking at what is f of negative x. So if I go to my original function definition, and I change my x to negative x, then I have negative x divided by the square root of negative x squared plus 2. So on top I have negative x. On the bottom, if I square that negative x, then I just have x squared plus 2. And notice what I ended up with when I simplified. If I pull that negative from the numerator just out to the front, negative x divided by square root of x squared plus 2, then I have the opposite of my original function. In other words, I have negative f of x. So in other words, when I change the sign of my x, it changes the sign of my function value, which means that we have f has origin symmetry. In other words, we're dealing with an odd function here, something that's going to look more like x to the third, or a cubic function. Okay. Now we want to determine asymptotes, and we have really three different kinds of asymptotes that could happen. We could have vertical asymptotes, horizontal asymptotes. We could also have slant asymptotes. So I'm going to start with what I think is the easiest, the vertical asymptotes. And we know that we have vertical asymptotes if our function is undefined. Well, our original function would be undefined if its denominator was equal to 0. So we have a vertical asymptote where the denominator, square root of x squared plus 2, is equal to 0. Square both sides, I get x squared plus 2 equals 0. If I subtract 2, I get x squared equals negative 2. And at this point, we should recognize that we have an issue, because in order to to solve for x, I'd have to take the square root of both sides, which would mean I would get a non-real answer. So in this problem, there is nowhere where the function is going to be undefined, nowhere where the denominator is 0. So therefore, there are no vertical asymptotes. Finding the horizontal asymptotes is going to be a little bit different. Typically, we find the horizontal asymptotes by looking at the degree of the numerator and the degree of the denominator. And in this case, it's a little bit more difficult to do that because our denominator has a square root of x squared plus 2. So instead of looking at this as a ratio of the coefficients, or the bottom is bigger so it's approaching 0 or something like that, instead we're going to go back to what a horizontal asymptote really is. And before, when we were discussing limits, we said that a horizontal asymptote is a value that our function approaches as our x's increase or decrease without bound, as our x's approach positive infinity or negative infinity. In other words, I want to know, what is the limit as x approaches positive infinity of x divided by the square root of x squared plus 2? If we tried to just evaluate this using infinity, we would end up with one of our indeterminate forms, infinity over infinity. So we need to change the way this looks. And previously I told you guys that one of the easiest ways to do that is to divide everything by the highest degree of the denominator. In this case, the highest degree of the denominator, we're going to say, is the square root of x squared. So I'm going to take my denominator, x squared plus 2, and I'm going to divide it by the square root of x squared. I'm also going to do that with my numerator, but before I do that, I'm going to think about what the square root of x squared means. If I'm dividing something by the square root of x squared, the square root of x squared is actually equal to the absolute value of x. And the reason for that is, if we have a positive value for x and we square it and take the square root, we would get the same thing as if we have a negative value for x. If I put in a negative 1 and square it, I get 1, and then take the square root, I'm going to end up with 1. So the square root of x squared basically acts like the absolute value function. Whatever the number is, positive or negative, it disregards the sign. You're always going to get a positive value. And if you'll remember from before, we said that the absolute value of x is equal to x if x is greater than or equal to 0, or it's equal to the opposite of x if x is less than 0. In other words, if x is negative, change the sign. Well, in our limit, we're looking at the limit as x is approaching infinity. If x is approaching infinity, then the square root of x squared, the absolute value of x, would have to be x, because we're definitely talking about values that are larger than 0. If we're approaching infinity, we have x values that are bigger than 0. So rather than writing this as the square root of x squared, I'm going to simplify it using my definition of absolute value. I know that that's going to be x. So now I have the limit as x approaches infinity, x divided by x, which is 1, over the square root of x squared divided by x is 1, plus 2 over x squared. As x approaches infinity, this term approaches 0. So I have 1 over the square root of 1, which would be 1. Now I need to know what happens on the other end. What happens on the negative values? So now we look at the limit as x is approaching negative infinity of x divided by the square root of x squared plus 2. And I'm going to manipulate this the same way. I'm going to divide both the numerator and denominator by the square root of x squared. So when I do that, I have the square root of x squared plus 2 divided by the square root of x squared. And then I have x divided by the square root of x squared. But now, again, saying that the square root of x squared is the same thing as absolute value of x, this time x is approaching negative infinity. So now we're definitely dealing with values that are less than 0. So if we're approaching negative infinity, the square root of x squared would be negative x. Oh, I forgot my limit here. I want to forget that. Limit as x approaches negative infinity. Negative infinity. So now I have the limit as x is approaching negative infinity of negative 1 divided by the square root of 1 plus 2 over x squared, which would give me negative 1 over the square root of 1, which would be negative 1. So our horizontal asymptotes are at y equals plus or minus 1. We actually have 2. On the positive end, we're going to approach positive 1. On the negative end, we're going to approach negative 1. Parts D and E on the next page want us to find the relative extra in intervals of increasing or decreasing, and the inflection points in intervals of concave up or concave down. That's what we've been working on in this unit. So what I'd like to do is I'd like to stop the video here and have you guys see if you can answer parts D and E, and go ahead and see if you can put all of those values together with what we just did here to come up with a sketch of what this graph might look like. So once you've done that and you're ready for part 2, go ahead and start that video.